It started now, so everybody can hear us, just so you know.
Okay, and you can see my screen.
Yeah. Yeah, now I see it in presentation mode, so we're good.
Okay, so we've got 10 minutes till the start.
Yes. So if you want to mute yourself locally or on there, I'll make a couple of announcements here in the next 10 minutes, just letting everybody know we're going to be starting soon. And then at the top of the hour, I'll do a quick little, housekeeping, do a quick little intro, and you've got a bio slide you're going to cover for yourself, right?
Yeah, I can cover it.
Okay. I wasn't able to download the PowerPoint for whatever reason. It's giving me an issue this morning, so I'll just kick it off quickly, turn it over to you, and I'll let you do your thing.
Okay, well, luckily the technology seems to be working today, so that's no problem.
Perfect. All right, I'm going to mute myself for a few, and I will talk to you shortly.
Okay, I'll talk to you at the top of the hour.
everyone. Thank you for those who have already joined the presentation. We're going to get started live here in about 5 minutes. I did want everyone to know who was already with us that everyone is muted. So if you're experiencing any technical issues or need to reach out to us, please use the chat function. Thanks, and we'll start again in about 5 minutes. Hello, everybody. Good morning, good afternoon, or good evening, depending on where you're located. My name is Matt Munson. I want to welcome you to our most recent webinar. Today, we're going to be covering gas chromatography as used for online DGA. I did want to cover a couple of housekeeping items before we get started. Everyone is currently muted, so those who have already joined the presentation are muted. We are recording the presentation, and a copy will be emailed out to all of the attendees probably about 24 hours from now. We will have live Q&A, so questions will be answered at the end of the presentation. So please use the questions or chat functionality if you do have questions. You can send them during the presentation, and we'll come back to those once the live piece is concluded. I'm joined today by Donald Skelly, who is our product manager at Qualitrol for the dissolved gas analysis line, and overall a real expert in the field of DGA. So I'm pleased to be joined by Donald today, and again, we'll take questions from him at the end of the presentation. So without further ado, Donald, please take it away.
Okay, thanks, Matt. Yeah, good morning, good afternoon, good evening. I should start by saying that Matt is based in New York, so it's 4 a.m. for him. So thanks for setting this up, Matt. Yeah, so the presentation this morning is going to be probably about 30 minutes. Just looking at gas chromatography technology for online dissolved gas analysis. It was for multi-gas online dissolved gas analysis, the first technology used in the lab and continues to be the only technology. But for online, it was also the first technology deployed online. So we're going to take a look at the technology and at the application, the online application, and then just some attention points or some things to note about the use of gas chromatography. So this is just to introduce myself. As Matt said, I'm product manager with Qualitrol. I have responsibility for the dissolved gas analysis product lines that Qualitrol runs. So this is multi-gas and single gas product lines. And I've been working in this field for essentially all of my career. I joined Qualitrol in 2013. And the focus, of course, of the product manager is trends in DGA technologies, applications, and markets. I'm based in Ireland. Qualitrol's DGA facility is based in Portland, Oregon. Just to give a very short introduction to who Qualitrol are, for anybody who's not familiar, Qualitrol are a company formed in 1945, but they started to expand pretty dramatically in the 1990s. They now have 6 acquisitions, which are listed here, right? So Qualitrol are based out of Fairport, New York, but Beaverton, Oregon has serveron, and serveron were acquired in 2012, and they specialize in dissolved gas analysis. Qualitrol, of course, also have fiber optic temperature sensing, they have partial discharge monitoring, and they have power quality monitoring, etc. So the contents of this presentation, first of all, an introduction to the principles of operation and common applications for gas chromatography, and then a couple of slides just looking at the deployment of GC for online analysis, as opposed to offline. Online dissolved gas analysis, we then look at oil sample extraction, and gas analysis. 2 slides in diagnostics, the benefits of using gas chromatography, and there are quite a few. Attention points, other things to note about using gas chromatography, and then conclusions. On the right-hand side, the photograph is of a serveron dissolved gas analyzer. This is an online system situated beside the transformer, collecting oil samples and taking and performing dissolved gas analysis on a scheduled basis. I should say there are other systems out there other than the serveron one, but serveron were first to market with gas chromatography for dissolved gas analysis. First of all, some background, the basic principles or system architecture for a dissolved gas analysis system. So you've got a number of key components. You've got a carrier gas, and this carrier gas is usually one of the noble gases. In the case of our system, it is helium. In the case of laboratory systems, it is normally argon, but also can be helium. There's a regulator or a flow controller to regulate the flow of helium out of the cylinder. There is a place to introduce a sample, and in our case, it's a sample of the gases that have been extracted from transformer oil, but there are many applications for gas chromatography outside of of dissolved gas analysis, and I have a slide just showing a few of those. There is a column, and this column is, as is illustrated here, is a long tube. It can be stainless steel, it can be glass, it can be very, very narrow bore in the form of a capillary tube, or it can be wider bore, perhaps 1 millimeter, in the form of a stainless steel tube. It is contained inside an oven, and that oven has some thermostatic programming. So it's either held at a static temperature, or its temperature is raised or lowered depending on the application. Then at the end of the column, there is a detector to detect the gases, and there is, of course, some way of reporting it out, illustrated here with the screen. This is what a typical laboratory system looks like. So on the right-hand side is the output, the screen with all of the quantitative and qualitative data. And on the left-hand side is the gas chromatography system itself. So up high, it shows the injection system. And then the main gas chromatography system is dominated by the thermostatic oven. So the oven in which the column is contained. And this is just the inside of a serveron unit for illustration of what it looks like as an online system. There is a sample preparation and injection system here. And what is marked here with the badge TMX is essentially the oven and the detector system. It may not be possible for you to see, but it is lined with insulation. And this is to help keep it at a stable temperature, as of course is the oven in a laboratory GC, and thermal control is achieved in there. And then, of course, in the online system, there is a range of control electronics and communication. What's not shown on either the top or bottom photograph is the calibration, sorry, the carrier gas. So the carrier gas will be a cylinder connected directly into the laboratory system or into the online system, and supplying it with carrier gas, in one case helium, in the other case argon. The basic principles of how separation and therefore quantification and qualification of your dissolved gas sample is achieved. There is a mobile phase. In our case, it's helium, and there is a stationary phase, and this is a solid material which the column is packed with. So it can be a number of different compounds, and they're usually proprietary, or they are specific for the application. But if you were to see it, it's a powder type material. And essentially, as the mobile gas phase flows through the column, it will push anything that is in the column that can move. It will push it down through the column. So weakly retained substances move quickly through the column and come to the detector first, and strongly retained substances move more slowly and will come to the detector later on. And what you get is you get a time-based chromatogram. So at a specific point in time, one gas will be eluted and will hit the detector, and later, separated in time, the next gas will come hit the detector, then the next gas, and then the next gas. And what you get, therefore, is you get qualification. So by virtue of the time that the gas sample that's introduced at the start gets to the detector in its individual separated components, you know what that gas is. And of course, then on the next slide, I'll show you how you know how much of it there is. So you can determine how much of it there is based on calibration. And one of the features of gas chromatography is that it should be and it must be calibrated on a routine basis. In a laboratory environment, it's usually once or twice a week, and in an online system, it's the same, twice a week. This provides some distinct benefits, and I'll talk about those a little later on. So calibration, first of all, establishes the retention times of known peaks. And for dissolved gas analysis, we know what the gases are, right? We know that they're hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide, carbon dioxide, oxygen, and nitrogen. And that doesn't change. There are additional gases in the oil, but those are the diagnostic gases, or those are the key gases. So you establish a retention time of known peaks for those 9 gases, establish a relationship between known gas concentration and the peak area. So the size of the peak is directly related to the concentration. So that's where the quantitative element of the measurement comes in. So the time is the qualitative, and the size of the peak is the quantitative. And of course, it can be adjusted for changes in temperature and pressure. And then for measurement, so that's calibration. For measurement, you identify the peaks for the retention times in relation to calibration locations. So if you have the same gases in the measurement system as you had in the calibration system, which for dissolved gas analysis, we know what those gases are, and then we will see those gases being eluted at the same time. And if we look at the relative size and relate it back to the original calibration, we can get an accurate measurement of the quantity of the dissolved gases present. So we're talking today about dissolved gas analysis, but of course there are many applications for gas chromatography outside of that field, in the petroleum industry, in the chemicals industry, in forensics, blood alcohol, use of accelerants in arson, identification of drugs. Also used very extensively in environmental monitoring, and it's not specifically mentioned here, but used really, really extensively in pharmaceuticals. Gas chromatography in pharmaceutical laboratories, you could often find 20 or 30 systems under continuous operation. Used also for gas analysis. So there is natural gas, and then the one that we are interested in, which is transformer dissolved gases. 9 different gases, 7 of them considered diagnostic gases, and then oxygen and nitrogen, the atmospheric gases. I just noted here that if you reference any of the standards relating to dissolved gas analysis for transformer oils, they of course call out gas chromatography as the analytical technique to be used. So that's IC, American Standard Test Methods, and IEEE. And going through those standards, they all detail the use of gas chromatography. So it is the established technology for dissolved gas analysis. It's not the only one, but it is the original one, and it does provide some unique benefits. From the point of view of the application of dissolved gas analysis, some of the things that need to be considered is how many gases you wish to measure. So we could consider that ideally you would measure all 9 gases, but there are cost implications to doing so. So there are other different combinations of gas. For online dissolved gas analysis, some of the common applications are the measurement of just hydrogen as a general indicator of something happening or some fault developing in your transformer. It's considered to be an indicator gas or an alarm gas. If you see hydrogen being produced in appreciable amounts, you know that something is happening, and that can raise an alarm. Gas chromatography generally is not used for this simply because of the cost implications of using gas chromatography. So usually it's a single gas, solid state sensor type system, and serveron have one of those called TM1, but it's not GC. Then for gas chromatography applications, or for multi-gas applications, you would perhaps look at methane, acetylene, and ethylene, which would give you Duval's triangle number 1. If you add in or combine ethane and hydrogen, you get the other Duval triangles, and you also get to use the Duval pentagon for diagnostics. Add in CO2 and carbon monoxide for additional insulation. So this is in relation to the breakdown of the paper insulation. And then, of course, the atmospheric gases, nitrogen and oxygen. The serveron products and gas chromatography products in general can measure all of these gases and can measure them all on a single detector. And can measure them all on a single detector with reference to a recent calibration. Other things to consider for online DGA, physical and communication access. So there needs to be some way of connecting to the monitor, connecting oil connections into the monitor, and getting data off the monitor. Supply and maintenance requirements. So you got to be able to maintain this product. In the case of gas chromatography, there are considerations in relation to calibration and carrier gases, for example, and you've got to have access to the monitor and a mechanism to manage those. You got to consider the required accuracy, precision, and reliability. So it's not sufficient to achieve all of the above. You got to do it with some specified accuracy and with some understandable level of reliability. So then just an introduction to online dissolved gas analysis. So the first thing you got to do is you got to collect a sample of the oil. There's two ways that this is traditionally done with online monitors. It is normally automatically online sampling, or alternatively, if you're sending a sample for laboratory GC analysis, it will be manual sampling, often into a glass syringe or some other type of sealed container. You got to get the gas out of that sample. So gas extraction is the next element of that. In the laboratory traditional method, it would have been vacuum extraction, not used that much anymore, replaced in a lot of laboratories with equilibrium headspace gas extraction. And indeed, equilibrium headspace is used with some of the online systems. With the Qualitrol system, it's a membrane or tubular extraction. So the use of a semi-permeable membrane to extract the gases out of the oil phase into a gaseous phase. The next thing to consider for online DGA is the analysis of that gas. So you've collected the sample, you've extracted the gas out of the sample, and now you're going to analyze it. Gas chromatography is the technique used in the laboratories and the technique used in the Qualitrol products. But infrared spectroscopy can also be used, and there are multiple variants of how infrared spectroscopy is deployed: photoacoustic spectroscopy, ND, or non-dispersive infrared, NI or near infrared, and others. Or there are solid-state sensors, although generally solid-state sensors are limited to one or two gases and cannot provide the full range of gas measurements. And then, of course, once you have measured the gas, and ultimately this is the intention of online dissolved gas analysis, it's really all about diagnostics. So you look at thresholds, at rate of change, at ratios of gases. There are Duval triangles and pentagons that are universally known as a technique for interpreting these results, because ultimately what we are not trying to do here is to gather data on ppm, parts per million of dissolved gas. We're trying to interpret what's the condition of the transformer or the piece of electrical equipment. So diagnostics is, of course, the ultimate goal of all online or offline dissolved gas analysis. Just to go into a little bit more detail on some of the points in the last slide. So oil sample collection. Typically, for an online system, it will be continuous. Oil will be pumped through some type of a closed loop. Oil being taken out of the transformer at some sampling point, illustrated here by a high-level sampling point, through a monitor, and then pushed back into the transformer. And this is usually a continuous process, right? So you've always got fresh oil going through the monitor for analysis, or for gas extraction initially, but ultimately for analysis and ultimately for diagnostics. It happens with online monitors continuously. Different monitors have different default measurement frequencies between 3 hours and perhaps 8 hours. So you would get a DGA result something between 8 times a day and 3 times a day. And in fact, generally they can be increased or decreased in frequency. So you can get a result once an hour, 24 times a day, or as little as once a month. But for online dissolved gas analysis systems, it's typically 4 to 6 results per day. One of the big benefits of this is that there is no manual handling of the sample, because manual handling and collection of the samples can introduce some error, and that's avoided. The oil is contained within a closed loop system, very little opportunity for any interference from external conditions, and it is a very, very repeatable process. And the major advantage, of course, is that if you contrast this with manual sampling, where an individual goes to site, collects a sample using a described technique, but 2 different individuals will collect slightly different samples, and then it's transported to the lab, and then in the lab it needs to be handled again according to standard procedures, but different individuals will result in different outcomes. This online system is completely automated and has minimal variability. For gas extraction, there are a number of methods that I've already mentioned. The one used in the Qualitrol device is membrane or tubular extraction. So gas permeable tubes isolate oil flow from extracted gas volume, and it's illustrated here, oil in yellow and gas phase in blue. And essentially there is no mixing of the oil into the gas phase. So what you have is you have an isolated gas phase and you have an isolated oil phase. The gas can move through the walls of the tubes that form part of this membrane extraction system. The big benefit of using this type of a system is that you do not put the oil in contact with the atmosphere. So the oil does not get an opportunity to absorb any of the atmospheric gases, carbon dioxide, oxygen, nitrogen, and indeed moisture. By keeping it isolated in this tubular membrane extraction system, the oil that goes back into the transformer is not contaminated with atmospheric gases. It's a sealed system, and that physical barrier prevents liquid oil or aerosol transfer into the gas phase, but it also prevents atmospheric air from going into the oil. So for gas analysis, I also mentioned that there are a number of different techniques: gas chromatography, solid-state sensors, infrared spectroscopy. But of course, we're here to talk about gas chromatography. So gas chromatography is highly selective with complete separation of the gases of interest. And what this means is that individual gas amounts do not influence detected concentrations of adjacent gases. So as you send the gas sample down through the GC column, each gas is physically separated from the adjacent gases, and what comes to the detector is a pure sample of the particular target gas. So it means that there is no effect on the measurement of one gas from the measurement of adjacent gases. And that is something that you see with infrared spectroscopy, and often is something that you see with solid-state sensors, that they have some type of cross-sensitivity or some type of interference from one gas to the next adjacent gas. That's avoided completely with dissolved gas analysis, with gas chromatography. And that is the key to why gas chromatography is used in all of the laboratories. So globally, all laboratories that do dissolved gas analysis will use gas chromatography for this specific reason. And because you get complete separation, you can have complete and demonstrable confidence in the accuracy of the measurement. You have isolated the gas and you're measuring the gas in an isolated form. Single technique that measures all DGA target gases. So I mentioned there were many different techniques, there were many different applications for gas chromatography. For the dissolved gas analysis application, where there are 9 gases, a single detector can be used to detect all of those gases. And that again is driven by the fact that gas chromatography separates those gases. So there is no need for separate detection techniques or for other mechanisms for quantifying the gases, because you physically separate them, and that makes measurement a much, much simpler proposition. Employs high purity carrier gas and no atmospheric gas interference. Again, this is a double-edged sword. So you've got to provide the carrier gas in the form of a bottle of helium for the Qualitrol product. But it does avoid the sample of oil ever getting in contact with the atmosphere, and it also avoids the possibility of local contamination. So we're talking about perhaps smog in an urban environment, or car fumes from a nearby car, or leaking sulfur hexafluoride from a circuit breaker nearby. All of these can influence infrared-based systems because gas chromatography essentially is completely self-contained with its own supply of carrier gas. There is no interference from external atmospheric conditions. And gas chromatography provides routine minimum detection limits of about 1 ppm for most gases. And this is not uncommon for a lot of the techniques. But 1 ppm is applicable for dissolved gas analysis, right? We have a need for usually detection in the tens to hundreds of ppm for diagnostic purposes, but most of the standards will call out 1 ppm as a lower detection level. The major advantages of gas chromatography for gas analysis is that it can be routinely field calibrated. In the case of online DGA systems, that is once or twice per week. The real benefit that provides is that you're always operating off a recent calibration. For systems that cannot be calibrated in the field, you are operating off a calibration that may be a number of years old. And where it is necessary to make some critical decision about your transformer, a calibration that is a number of years old may not provide you with the confidence to do so. Gas chromatography is the international laboratory standard method for the reasons that I've already described. And because all of those diagnostic techniques, Duval triangle and pentagon, which I'll illustrate in the next slide, they're all based off data which was collected with gas chromatography. Then you have better possibility of alignment. So the data that you're getting from your online system, ultimately, you don't care about ppms, you care about diagnostics. And because this is the same technology as is used in the lab, the possibility for high quality alignment between the diagnostic system and the data that you get from an online GC system is increased. This slide is just an illustration of one of the diagnostic techniques. I'm sure most people on the call are familiar. It's Duval triangle. And there are 3 triangles for the application of main tank transformer oil, transformer oil for mineral oil. And there are 2 pentagons developed also by Duval and released in the last number of years. The triangles have been around for well over a decade. The pentagons have been around for a shorter period of time. And basically, they all build upon what's provided in the previous one. So the Duval triangle number 1 was, as the name implies, the first one released, and it gives you a capability to look at diagnosis of your transformer on the basis of 7 different possible conditions. So they're shown in the top right hand side. The blue area is discharges of low energy. The pink is discharges of high energy. Light blue, mixed pulse, etc. So as the coordinate points of those 3 gases, where they intersect, of methane, ethylene, and acetylene, where those points interact, indicate the presence or absence, indicate the nature of a fault. In the case of Duval triangle, they don't necessarily indicate the presence or absence, because those 3 points will always intersect somewhere, and therefore there are further considerations over and above the intersecting points. But this is designed as a quick reference that allows you to understand the otherwise list or table of ppm data. This allows you to align this with some possible diagnosis. The pentagon does something similar. It just adds a greater degree of of understanding or of refinement over and above the triangle one. It does not replace it, it just adds additional information. The Pentagon 2, oh, so just jump forward. Pentagon 2 does something similar. There are other methods of looking at this. Qualitrol have a system licensed from a utility in the US called Tone, and it's an artificial intelligence type system. And what it does is it looks at a library of failures, many hundred transformer failures, and using artificial neural networks, it will map the data coming from your transformer or from the transformer under test with this library of transformer failures and autopsies, and it will give a live indication of the presence or absence of a fault and the severity of that fault. And shown here, it's just scrolling through some data taken from a serveron TM8, and it's showing a severe fault, the nature of the fault being overheated oil and low energy discharge as you scroll through it. This is a graphical representation of Rogers ratios. Again, it's a coordinate point looking at 3 different gas ratios and presents then a diagnosis. And all of these graphics are contained within the software that you will get with an online DGA system. So this is what you see with the Qualitrol system. Other systems will likely incorporate most of these diagnostic systems in a similar graphical format. The one unique to Qualitrol will be the one on the bottom right-hand side, which is Tone, and that's the artificial neural network system. A very powerful system for understanding and for alarming based on a diagnosis rather than based on parts per million or based on rate of change. This will alarm based on an actual diagnosis. Okay, just a couple of slides left. So the benefits of using online GC for DGA, the primary one is accuracy and certainty in that accuracy. So you're operating off a fixed calibration point that has been determined in the last number of days. And you're also operating in an isolated environment. So you have your own carrier gas. You're not influenced by external factors. IEEE IEC 60567 specifies that accuracy for DGA must be plus or minus 15% or better. So in reality, this would mean that a measured result or an actual concentration of 100 ppm might be reported anywhere between 85 and 115 ppm. And this is for laboratory conditions. Online gas chromatography, because you remove the whole element of sampling of the gas, a sampling of the oil and taking it to the laboratory, can typically achieve verified accuracy of plus or minus 5%. And verified is highlighted there because it is based off a calibration that has been performed in the very recent past and therefore can be considered verified. And then, from the point of view of accuracy, accuracy cannot be less than the lower detection limit. So if the lower detection limit for these gases is 1 ppm, then accuracy cannot be greater than that, because that describes what the resolution of the product will be. And down at those very low levels, accuracy might be dictated by the lower detection level rather than the plus or minus 5%. And this has implications for diagnostics. So if we look at, and this was a slide that was very generously provided by Michel Duval to Qualitrol, this shows the implications of reduced accuracy. So at plus or minus 15%, which is typical of a lab, you will see that there is in fact a range of locations where the coordinate points can be. And depending on that range, you may or may not find yourself in a single diagnostic space. And certainly if you increase to plus or minus 30% accuracy, which is typical if the sample collection is poor quality, you may find yourself moving from one diagnostic space to another, essentially resulting in the possibility of false diagnosis. What's shown in the blue dot is the actual coordinate point But for an online GC system, at plus or minus 5%, you're going to be very, very close to that central coordinate point, and therefore very, very precise in your diagnosis, which is ultimately the definition of what dissolved gas analysis is about. If accuracy really is of poor quality, or you're down at very, very low concentrations, then the areas can get very, very large, to the point where, you know, if accuracy at a level of 2 ppm is plus or minus 75%, you cannot necessarily rely on any diagnosis. And that's why Duval triangles and pentagons should be used only when concentrations start to get appreciable, so in the tens or hundreds of ppm. Because at very low concentrations, where you're driven by lower detection limits, inaccuracies can lead to inaccurate diagnosis. Things to note about the use of gas chromatography. So the first is, and I've already mentioned it a couple of times, you do need a carrier gas, right? So this is something which has to be managed. Online or laboratory GC requires this high purity carrier gas. Usually it's something of the order of 99.49 purity, so 99.9999% purity. It's not difficult to get this. It's available in all countries and from many different gas manufacturers, but it is required. For online DGA, the most popular carrier gas is helium. But while this needs to be provided and needs to be managed, in actual fact, modern gas cylinders contain enough helium to supply an online monitor for about 15 years. And in actual fact, that would be at a 6-hour measurement cycle. If you move to an 8-hour measurement cycle, it would supply gas enough for 18 years. So the provision of gases is something that needs to be managed, but it can be managed on day one when you're installing the monitor, to provide what will essentially likely be a lifetime of gas. Calibration gas is another thing that's required for online gas chromatography, and all of the benefits that calibration provides. So accuracy and certainty, not just on the day of installation or in year one, but over the entire lifetime of the monitor. That's what it provides. It provides certainty that you're operating off a known standard, physically traceable physical standard. Gives you confidence then to perform diagnosis and to make decisions about your transformer. Modern cylinders have a shelf life that is something of the order of 5 years, and replacement of that cylinder will be dictated usually by the shelf life, by the expiry date on the cylinder. So roughly 5 years. For Qualitrol, and I think this may be the final slide, or the second to last slide. So there are 8,000 online GC units installed globally, and that's by Qualitrol. There are other manufacturers out there, so that number is even greater. Very, very well-established technique. It's been around as a field-deployed instrument since 2004, and in the case of Qualitrol, there are more than 8,000 in the field. It's used in more than 100 countries, ranging from all geographics. So from northern Canada or Siberia, there are many monitors in the Middle East or in the deserts of North America, and indeed in the tropics, Central America, Indonesia, Philippines, etc. So suited to a wide variety of climates. For online gas chromatography, because the key analysis occurs within an oven, it's operated hot. So the TM8 from Qualitrol is able to operate in all of these various different climates with the need for nothing but a heater. This means that this can be done, this system can be operated without any need for external fans or any need for heat sinks. So there's no need to dump heat out of the monitor, because the monitor operates hot continuously. This allows for IP66 protection, because you can have a completely sealed system. There is, of course, no influence from atmospheric contamination or weather, because the system is sealed from a gas perspective also. And GC technology is immune to the effect of oil aging. So as transformer oils age, they don't just produce these 9 target gases. They produce many, many other gases, many, many other compounds, volatile compounds in the oil, alcohols, for example, but many compounds. Gas chromatography does not see these because it physically separates the components before sending to the detector. It is immune to the presence of other contaminants in the oil. And finally, the conclusion. So gas chromatography is the default technique for laboratory DGA. It's the technique that underlies all transformer diagnostic techniques, and all transformer diagnostic techniques. What I'm saying here is that they're all based on data collected from laboratory gas chromatography systems, and therefore the alignment will be much better. Online gas chromatography requires carrier and calibration gas, and this ensures accuracy and protection from environmental pollutants. And of course, in the case of carrier gas, can be provided in a cylinder that will give carrier gas for the lifetime of the product. Accuracy of dissolved gas analysis is a key driver of accurate diagnosis, and ultimately the reason that online dissolved gas analysis is put in place is not for measurement of ppms, it's not for rate of change, it's not for trending purposes, it's for transformer diagnostics. If you want to perform accurate transformer diagnostics, you need accurate data. And for all of the reasons shown in the presentation, you get accurate data from gas chromatography. That's my final slide. Matt, if you can open it up to questions, or perhaps there have some questions have come in. I think Matt mentioned at the start that any questions that you had, you could send in via the chat function. I'll hand it back to you, Matt.
Yes, sir. Thank you very much. So, as Donald said, we will open it up for Q&A. We do have a few questions, and we'll give folks a couple minutes to put some more through into the system. Did just want to reiterate, we did record the presentation, and we'll email out a copy of that. Also, Donald mentioned some of Mr. Duval's work. We were lucky enough to have him give some presentations in the last few years for us. So we'll also include a link. Some of those are available in our resource library. So, and if there's any additional questions that you do come to as you're going back through the presentation, just reply to the email that you get from us, or you can always contact us at info@qualitrolcorp.com. So going back to a few of the questions we had, how often do you have to change the carrier gas to perform continuous measurements?
Okay, so it depends on the rate of measurement. So I mentioned earlier on, at a 6-hour measurement sample, there are now cylinders available which will provide 15 years of carrier gas. If you move to an 8-hour measurement cycle, that'll get you up to 18 years. If you move down to 1-hour measurement cycle, so dissolved gas analysis, once per hour, a little over 8,000 DGAs in a year, that same cylinder of gas will last you something of the order of 5 years. There are other cylinders, and that depends on the cylinder you use, right? So there are high capacity cylinders, which is what I'm describing there. There are other regular capacity cylinders that will give you something between 5 and 7 years at that sort of 3 measurements to 6 measurements per day frequency. So it very much depends on the cylinder that you use, and it also very much depends on the frequency of the measurement. But at, let's say, a common measurement frequency of once every 6 hours, 4 times per day, you'll get something over 15 years from a high capacity cylinder of helium.
Another question, aside from, carrier gas, how often do you need to maintain the system?
So there, apart from the carrier gas, which is driven by measurement frequency, the GC columns themselves are also a service item. So that's also driven by the frequency of measurement. On a 4 times per day or once every 6-hour measurement cycle. There will be a service required for the GC columns somewhere between 5 and 7 years. For the calibration gas, so the calibration gas has sufficient volume to last for between 6 and 8 years, but it has a shelf life of up to 5 years. So at a 5-year service interval, you would need to change the calibration gas. Now, it also depends on the gas that you use. So there are 2 different options, one with a 3-year shelf life and one with a 5-year shelf life. So it depends on the frequency for the GC columns, the frequency of measurement, and then it depends on the cylinder of calibration gas that is used on whether it's a 3 or 5-year interval for that gas.
Okay. Another question about the carrier gases. Do they need to be cooled if installed in hot countries? There needs to be no cooling employed. So this monitor can operate under ambient conditions of up to plus 55 degrees centigrade in full sunlight, and there is no need for any cooling. The cylinders of carrier gas are rated to withstand temperatures in the range of 250 to 300 degrees centigrade, and that of course is not ambient conditions under any circumstances. That would be conditions where, for example, there would be a substation fire, and in actual fact, the modern cylinders have a safety disc, a burst disc, that in the case that you get those extreme conditions, the cylinder will vent safely. But there's no need for any cooling of any type with online GC systems. There is a need for heating because it operates hot, and there is a heater within the system that will maintain it at operating temperature anywhere down to negative 50 degrees centigrade. The measurement range for this product is plus 55 to negative 50, and in that entire 105 degrees centigrade measurement range, you will still get plus or minus 5% accuracy. Another question about the carrier gas. How much is used in each analysis?
I have a table. I didn't put it into the presentation here, so I don't know. We're talking about in standby mode, the monitor uses approximately 1 milliliter per minute. In active measurement mode, and if you imagine that you're doing a sample once every 6 hours, you will have 1 hour of active measurement mode, and you will have 5 hours then of standby mode. In active measurement mode, I believe it's something approximately 5 to 7 milliliters per minute. The standard capacity cylinder contains 7,000 liters of gas, and that will last you between 5 and 6 years. I do have a table, and if the person who sent in that question wants to drop us an email, I will send them the table that shows the quantity of gas being consumed, or indeed for anyone who's interested and wants to drop us an email, I will provide the table. But again, it comes back to, and I guess this is the relevance of that question. It comes back to how long a cylinder will last. So a standard capacity cylinder on a 6-hour measurement cycle will last 5 to 6 years. A high capacity cylinder will last between 15 and 18 years.
Okay. There's a few questions that are similar, so I'm going to paraphrase, and if it doesn't address what folks are looking for, let us know. Is this more applicable to the monitoring itself? Is it more applicable to a new build or something that we're retrofitting?
It's perfectly suited to either. So the monitor can be installed on the transformer if it's part of, let's say, a new build, and for convenience, the OEM would want to mount all monitors or all systems on the main tank, on the tank themselves. So it's suited to tank mounting. It's also suited to retrofit on I guess, if possible, on the tank mount, but also on a pedestal mount, which we have as an option. The big benefit that you get from use of gas chromatography in retrofit applications is that as transformer oils age, so they spend many years in transformers, being heated and cooled. Part of that aging process breaks down the oil, and it breaks down the oil into the gases that we want to measure, but many other things. And those are essentially, from an analytical perspective, to be considered as contaminants. So this could be propanes or butanes or hexanes or alcohols or other breakdown products in the oil. And in retrofit applications, these can be, quite considerable. There can be a lot of these interfering contaminants. Gas chromatography is immune to those. So what you will get from a gas chromatography system installed on a retrofit old transformer nearing the end of its life with dirty contaminated oil, and from a new build, brand new transformer, new oil, you will get the same plus or minus 5% accuracy. No influence from interfering or contaminant products in the oil. So it's suited for both from the point of view of mounting and installation, but it's particularly suited for both from the point of view of accuracy. Accuracy is unaffected by that application.
All right, speaking of accuracy, again, we've got a few different questions, so I'm going to try to combine it here. How do we guarantee that accuracy and reliability? And then as it relates to lab accuracy, let me just read that here. So if results of different labs will be within 15% bandwidth, would 15 sensors on the same transformer supply the same results?
So for gas chromatography systems, our accuracy is an absolute accuracy. So it's not an accuracy one monitor to the next. And therefore, to answer the second part of that question, 15 monitors on the same transformer will give results that have a span of plus or minus 5%. So it will be considerably better than you would get if you took 15 samples and sent them to 15 laboratories, or indeed took 15 samples and sent them to a single laboratory. The first part of the question, in relation to how that is achieved, we're limited in how we can prove that, or rather the user is limited in how they can prove it, because laboratory accuracy is limited to plus or minus 15%. Online system, essentially what you're getting is you're getting the same level of accuracy as you would get from a laboratory GC, but you're removing the influence of the sampling error. So the human element of collecting a sample, taking it to the laboratory, and then taking that oil from the collection chamber into the laboratory GC. A difficult one to demonstrate that, but I would say that the data would show it for itself. So with an online GC system, you will see data coming out that will have variability of less than plus or minus 5%, whereas collecting repeated samples from that same equipment and sending it to a laboratory will likely show that there is an influence from the sample collection, sample transportation or shipment, and then sample handling in the laboratory. So you'll see it in the data. You'll see much more stable data that will be in or around the data that you will be getting from the laboratory.
Okay, one question about, actually a couple questions here, I'll summarize. The number of measurements required per day as it relates to aging. You mentioned a chart, is that covered on there? I'm not sure I fully understand the question. If it relates to recommended number of samples taken per day, I would say that metric has been sort of established by online DGA vendors as opposed to by any of the industry bodies. So Qualitrol serveron monitors ship out of the factory defaulted to 6 measurements per day, 1 every 4 hours. Other manufacturers default to 1 every 3 hours.
or 8 samples per day, and yet more manufacturers default to once every 8 hours or 3 samples per day. I don't think there's a hard and fast rule in relation to that. The measurement frequency should be a few samples per day with the capability then to accelerate. So if you see gases changing dramatically, maybe it's not yet time to take any service action or any action in relation to taking the transformer offline, but maybe you want better resolution. So you would have automatic ramp up of measurement frequency from, for example, once every 4 hours to once every hour. And the Qualitrol monitor can do that, and most monitors can do that, right? Some have limitations in that regard. They can only get to once every 3 hours, but most can get to once per hour. And really, it would be driven by the conservatism of the particular utility, or whether or not they wanted this very, very high resolution, or whether they were okay with 1 sample per day or 2 samples per day. It's a personal decision at a utility level.
Kind of following a line there, what alarms, either number or type, can be set for DGA?
So that depends on the system. With our systems, there are a range of different alarm set points that you can set, but they are based on parts per million of gas, or parts per million of total concentration of gas, so all of the gases together, or the rate of change, so the amount of gas that changes over a period of time. And there are guidelines from IEEE and IEC in relation to what those should be set at. With the Qualitrol system, we do have a unique application in the form of, and I showed a screenshot from it, in the form of TONE, which stands for Transformer Oil Notification and Analysis. And this system actually will alarm on a diagnosis. So it will tell you if you have a fault present. It will tell you the severity of the fault. And you can alarm on that rather than alarming on ppm or rate of change, which then requires you to go in and do a diagnosis. With the use of TONE, which is an option within our software, you can alarm on the actual presence of a fault. And what this does is, if you have a large population of monitors, let's say you have 100 monitors, then you might find yourself getting alarms for ppm of gas or rate of change of gas very regularly. You know, you might have to deal with 1 or 2 or 3 of these per day. And often they are, I won't say false alarms, but they are alarms that you then make a decision that everything is okay and you continue with normal operation. With the TONE system, it does not alarm on, let's say, on ppm or rate of change. It alarms on a combination of conditions that result in a diagnosis. So essentially takes that necessity away from the user to go and view the ppm data, view the rate of change data, and make a decision. And this artificial neural network system will give you an alarm on an actual fault. So different systems, but it's, again, a lot of it is driven at a personal decision-making level in a utility.
Perfect. There were a few questions we weren't able to get to as we come to the top of the hour. Some were very specific, so we'll reach out to folks offline to get those addressed. I did want to reiterate, we will send out a copy of the presentation, so if there were any questions that we kind of paraphrased together or we didn't answer up to anybody's questioning, please reply or reach out to us at info@qualitrolcorp.com. We'll be happy to take that. One last one, Donald, and then we'll let everybody go. We talked about some different diagnostic methods, Duval and whatnot. What is what is your recommendation for how people should use all of those and put them into their predictive maintenance program?
So I would say that all of those diagnostic systems should be used with a level of caution. For example, in isolation, the Duval triangles and pentagons will always give a diagnostic regardless of the concentration. So you must give consideration to the quantity of gas. Diagnosis when you have single-digit ppm of some of the gases it becomes a little driven by the lower detection limit type errors. And also, of course, a diagnosis of, for example, overheating oil when you have just 1 or 2 or 5 ppm of oil might be something that you would take no action on, because it's so small. Okay, you had overheated oil, but it may have been a very, very small or even isolated situation. I would say that using all of these together and giving consideration to them is the most powerful. So I think that, if you use Rogers ratios together with Duval's triangle, together with the key gas method, together with tone, you're likely to get the best insight into what's happening in your transformer. Michel Duval would probably say differently, but I would say that none is necessarily better than the other. In combination, it's a very, very powerful suite of diagnostic systems to allow you to get visibility into what is otherwise a black box, right? Otherwise a big metal box that you can't see anything in, and all these diagnostic techniques provide you little bits of additional information.
Perfect. Thank you for that, sir. And Donald, thank you for your time today to present on this. I want to thank everybody for their questions, a very lively conversation. And again, we look forward to seeing everybody at one of our upcoming presentations. And then again, please reach out to us with any questions that you may have, info@qualitrolcorp.com. So for myself and Donald, thank you again for joining, and we'll talk to you all soon.
Thank you very much, and thank you, Matt.